All right, so let me introduce you three great minds because you need to read their books and papers. First is Yuval Perez, David Aldous, and Russell Lyons. So today I want to just review some basic facts about Markov chains. As you know, the variation distance is just maximum of theta 1 of A minus theta 2 of A. A is inside I. But some people try to get some proxy because, for example, as you know, there are many different ways to define mixing. For example, Lowas uses his own mixing definition. Yuval Perez uses his own definition. So any mathematicians, because each one has a different need to solve a different problem, so they think that, okay, so my definition of mixing time could be easier for my problem, and so they go and work around that. And you may conjecture that, okay, so they may be related to each other up to some factor, and your conjecture is true. And many of these mixing times are related to each other, also relating to other concepts such as relaxation time that we will talk about. And so a measure of deviation from stationarity at time t, as you know, is just pi when xt is something and this is your stationary distribution. And you can also define the maximum of di of t. And because it is maximum, so you expect that your d of t is less than, for example, than d bar of t. 1 is less than 2, so 2 d bar of t is greater than d bar of t, everybody knows. But this is important. 2 d bar of t is greater than d bar of t. And there is a lemma that says even more general things, that d bar of s plus t, and d bar, I forgot to say that it's just the maximum of pi xt could be anything, minus pj xt. And this is less than equal to d bar of s, d bar of t. And for example, to prove some problems, to prove some proposition and theorems, you need to know that if you define, for example, the L1 norm of F1, which is always pi I f of I, and for example, L1 norm of V is just Vi, you should always know that the Cauchy-Schwarz says that the L1 norm is less than L2 norm. So geometrically speaking, so you see this distance is smaller. So the L1 norm is smaller than L2 norm. And now I want to prove a very beautiful lemma, because if you work on that, it's just the Cox formula, and Cox formula is just a simple corollary of that. So that's why this lemma that I will prove is important. For any t1, 2, etc., the probability that ta is equal to t minus 1 is equal to probability that ta plus, as you know, you are in set A, you go and the return time to A. Whenever you see plus, it means return time to that set, or if it is an atom, to that point. So when this is equal to t, so this probability is equal to pi of A times pi of A, probability that that t of A plus is greater than equal to t. And so the probability with respect to pi of A. And what is pi of A? Pi of A is just, for any vertex in your graph, it's just your, for example, pi of A as before, but we just normalize it to pi of A. So it's always a probability distribution. So the sum of that is just 1. It's easy to observe that. Now I want to prove only, because we don't have time, I want to prove only this part, which is very beautiful. So write this on a paper, and the proof is very beautiful because you see we have a set A. We start here. Okay, so at x0 we are at the set A, and then x1 it's because it's just a random variable. It could be out of A. At x2 it could be out of A. At x3 it could be out of A. It's just a random walk. At after some time, for example, after x at t times, it comes back to A. So we can compute this probability that the return time, if the return time takes t time, so if you add 1 step, 2 step, 3 step, all of them is just t step. If you add all of these time steps, it's just t steps. So this is by definition what I said. The story is that the probability that x1 is out of A and xt minus 1 is out of A. But suddenly here, xt is inside A. So how do we write this probability? Okay, so we might say that, as before, x1 is not in A, xt minus 1 is not in A, but we can exclude the fact that xt is not in A. Probability that x1 is not in A and xt is not in A. So if you just for example, if this term goes to the left term, then this is just that when xt is inside A, like this, and xt is not inside A. So it's just a simple probability. And now I want to write this in another form. I want to say that instead of x1 till xt, I want to say x0 till xt minus 1. Because the Markov property, it's just a sequence. It doesn't care about where you start. So you can say it's just the same event. So that event is just the same event. I mean, in the filtration, if you work on filtration, it doesn't matter, because filtration shows that it doesn't matter. So we can write this. And this is exactly pi of x0 in A. And the rest of them is not in A. For example, x1 is not in A, xt minus 1 is not in A. And finally, what is this? This is just pi of A, because it is independent. So this one and this one. Because these two events are independent, The first one is just pi of a. The second one, because it's a product of probabilities, because this event is independent of this event. So if you are in A, is independent on what this event is. So times, and we know this is the probability that if we start from PA probability, that the return time to A is greater than T. So it goes out after sequence, after some random walk, it goes to inside that. It goes out after some times, it comes back. So always draw pictures. You know, I see, when I see a mathematician doesn't draw a picture, I really don't enjoy reading that article. But when I see a mathematician writes some beautiful pictures like this, that a random walk, for example, a subordinated random works like this, and after a time it returns back to this, or it never returns, because if it touches some boundary, for example, at the boundary, it's just a sink, and it never returns. So you see, using these sketch, we feel better, we understand things better. So the corollary is that pi of a, this is the Cox formula. Cox is a great mathematician. Maybe there are just 50 mathematicians like Cox in the world. Cox is like Poincaré, Lebesgue, and those people. So pi of a, expectation of TA is greater than 1. Because it's just a simple observation of the lemma that I proved. So it says that the expected return to A is inversely related to pi of A. I just introduced the cover times, but I will talk about it later. Cover time, you know, Matthew has worked on that. Matthew's method is very popular. And the cover time is just the time required to visit every state in your graph. It visits this one. So the maximum of all of these, the maximum of all hitting these vertices like J, the maximum of all of these is just the cover time. So the worst case, how long does it take to hit the worst case, in the worst case? But the idea is how can we bound this expectation of C if we start with I in terms of mean hitting times or expectation of TJ. And I just say the result of Matthew without proof, that Matthew is popular because of this. The maximum of cover time over all vertices is just less than hn-1 times, this is just a constant, I will say that, and times the maximum over I and j hitting tj. And same thing as minimum of your expected cover time. The minimum is just greater than some constant as before. Now minimum of expected time to hit the j's vertex. And always I is not j. And as I said, this is just a constant, which is sum over 1 over m. So m from 1 to n-1. So it says that your cover time the maximum expected cover time can be bounded by expected heating time. And intuitively, it's easier, but we should prove it. But now I just want to jump in to another topic, which is creating a new Markov chain from an old Markov chain. And geometrically, I want to show you that if this set is A, then the first time, for example, you start from here, the first time that this random walk hits A is S0. The second time is S1. The third time, S2. So after several times, we are at Sn. It takes Sn times. So Sn is just the minimum of Sn minus 1, such that Xt is in A. And you start inductively with just time to hit A, as before. So it's just the minimum of Xt in A. So it reminds me the subordinated random walk or the subordinated Markov process. So it's just a transformation that we use, and the chain. I mean, we can create a new chain because we have an X chain. So we have an X chain. Now I want to create a new chain Yn, which is X of Sn. So your old chain evaluated at times Sn only. So, for example, you have a complicated random walk. For example, this is the coast of Britain, and you can approximate it by some lines. So these are the ideas of fractal dimension, and so it's like you want to evaluate it at some random times, to approximate your complicated random walk. What is interesting is that the probability, your transition probability, is just the probability that Xta after Ta, after this time, we hit J. So it's just the one-step probability, one step of all of these times. So the time that it needs to hit another vertex. So you can say that the stationary distribution of this new chain is just the normalized things that I talked about before, the normalized stationary distribution. So it becomes another distribution because sum of that is equal to 1. And one elementary thing that I want just to point out is that when we say reversible chain, it's just this definition. Pij is equal to pi j pji. And for example, pji could be 1 over degree of j. This could be degree of j over 2 times number of edges. This is 1 over degree of I. This is degree of I over 2 times number of edges. This goes out. Let's see. So 1 over 2m is equal to 1 over 2m. And this is, we call it detailed balance equations. And what is interesting is that this is just another way of saying that pi j is equal to pi I pij. The proof is very simple because pi I pij from reversibility is just pi j p j I, and just summation is over I. So